In this lecture, we will see the schematic diagram of a 2-input NAND gate and how to draw the layout from the schematic. So this is a two-input NAND gate. What's the symbol of a two-input NAND gate? The symbol of a two-input NAND gate is it has two inputs, let's say A and B, and the output is Z, and plus not gives NAND. So AND is A plus B plus not is the inverter, gives A plus B bar, or you can write it as A dot B bar. Now the truth table of a NAND gate is written as let's say this is the input A, B, and the output is 0. Input 0 0, output is 1. Input 0 1, output is 1. 1 0, output is 1. Or 1 1, output is 0. Now how you obtain this you will see later on. Now since this is A dot B bar, so when we have a dot operator we know that the NMOS will be in series and the PMOS will be in parallel. So the NMOS is in series and the PMOS is in parallel. Okay, now so there are two inputs. Since there are two inputs, we need two PMOS and two NMOS. Okay, now let's move to the schematic of a two-input NAND gate. First we'll see the normal schematic. Normal schematic diagram of a two-input NAND gate. Okay, so we know that the PMOS is in parallel and the NMOS is in series. So there are two PMOS. This is PMOS 1. This is PMOS 2. The sources of the PMOS, they are connected to VDD. So this is VDD. And the two NMOS are connected in series. Is connected to ground. So this is input A and this is the input B. This is input A, this is input B, and the output is obtained from here. Output is Z. This is our PMOS 1, this is PMOS 2, this is the NMOS 1, this is the NMOS 2. Now let's see the terminals. This is the source terminal of P1. This is the source terminal of P2. This is the drain terminal of P1. And this is the drain terminal of P2. This is the gate terminal of P1. And this is the gate terminal of P2. So this is the common drain of P1 and P2. So we know that the output is obtained always at the drain terminal. So this is the drain terminal of N1, source terminal of N1, and this is the gate terminal of N1, and the source of the NMOS is connected to ground. This is the source terminal of NMOS is connected to ground. So this is source of N2. This is the drain terminal of N2. This is the gate terminal of N2. Okay. So this is the normal schematic diagram of a 2-input NAND gate. Now, how will you test the schematic diagram of a 2-input NAND gate? The input is given at the gates, output is obtained at the drain. The inputs A and B are given at the gate terminals, that is gate of P1, gate of N1, and gate of P2, gate of N2. And the output is obtained at the drain terminal, that is the drain of P1, drain of P2, drain of N1. That is this point. Now let's see the truth table. How you have obtained the truth table of a 2-input NAND gate. So we'll see the explanation for the truth table. Okay, the first condition was when A is equal to 0 and B is equal to 0. So according to our circuit, or according to our schematic, when A is equal to 0, B is equal to 0, A input is given to both P1 and N1, and B is given to P2 and N2. So when A is equal to 0 and B is equal to 0, okay, when input, let's see the input, then the condition of PMOS and the condition of NMOS. When input is 0, PMOS is on, NMOS is off. When input is 1, PMOS is off and NMOS is on. Okay. So when A is equal to 0 and B is equal to 0, this P will be on and this P2 will be on, these two will be off. So P1 and P2 remain on and N1 and 2 become off. When P2 and P1 become on, so certainly there will be a short circuit for these two MOSFETs, and here there will be a open circuit. When P1 and P2 become short circuited, then how will it appear? Something like this. Similarly, over here, this is connected to VDD, and these two remain open circuited, connected to ground. So the output is at Z. So certainly, since these are open circuit and these are short circuited and this is open circuited, even this is short circuited, and they are in parallel. So if they are in parallel, when either of this is short circuited, then the output will be driven as VDD. So Z gives the value of VDD, or you can say it gives a high value. So in our case, high value represented by 1. So when input is A is 0 and B is 0, the output Z will be equal to the output Z will be equal to 1. Now let's see when A is equal to 0 and B is equal to 1. The second condition is when A is equal to 0 and B is equal to 1. So here same P1 N1 and here it is P2 N2. When A is equal to 0, P1 will be activated or this is on. When B is equal to 1, N2 will be on. So P1 and N2 will be on. P2 and N1 remain off. So now let's see what happens to the schematic. This is for P1. P1 will be short circuited. These two will be short circuited and these two will be open circuited. So this is short circuited, this is P1. Now P2 will be open circuited. This is same connected to VDD. This is P2, that is open circuited. Then N2 will be on, that is short circuited. N1 will be open circuited. So N1 is open circuited and N2 is short circuited. This is ground. This is N1 and N2. So now since there is an open circuit, so this will not work. And here this is short circuited and this is open. Even though this is open, since these are in parallel, the VDD, this VDD will seen in the output Z. So at the terminal Z or at the output you get VDD, or you can say you get a high voltage, or we represent the high voltage as 1. So when A is equal to 0, B is equal to 1, the output obtained will be is 1. So similarly, we'll see the next case. When A is equal to 1, when A is equal to 1 and B is equal to 0, similarly at A we have P1 and N1, at B we have P2 and N2. So when A is 1, N1 will be on. When B is equal to 0, P2 will be on. So P2, N1, they turn on. P1 and N2, they turn off. So if we represent in the schematic, P1 is off. So this is represented as open circuit. And since this is on, this is represented as short circuit. So P1 is off. So this is open, P1. P2 is on. So it is represented as short circuit. This is P2. This is connected to VDD. Now here N1 is on. So it is short circuited. And N2 is off, so open circuit. This is ground. This is N1 and N2. Since we have an open circuit here, then this will not work. And the same condition here. Here it is open circuit. Here it is short circuit. So even though this is open circuit, this is short circuit, this open circuit will not affect since the P1 and P2 are in parallel. So at the output terminal Z, we'll get VDD, or you can say high voltage, or you can say 1. So when A is equal to 1, B is equal to 0, the output obtained will be 1. Now the last condition, when both the inputs will be 1, when A is equal to 1 and B is equal to 1. Again here it is P1, N1, P2 and N2 for B. So when both are 1, both P1 and P2 will be off, N1 and N2 will be on. So P1 and P2, they will turn off, N1 and N2 will turn on. So when both are off, then this is represented by open circuit. When both are on, this is represented by short circuit. So here this is connected to VDD, and here both will be short circuited. So this is P1, P2, both short circuited, and N1, N2, this is open circuited, and both N1 and N2 are short circuited. Now the output obtained at Z will be driven from ground. So the output Z will be equal to low value or low voltage, or you can say 0. So when A is equal to 1, B is equal to 1, then the output obtained will be 0. Now after getting explanation for the truth table, now let's see the twisted schematic diagram of a 2-input NAND gate. So now we'll see the twisted schematic diagram of a 2-input NAND gate. Of a 2-input NAND gate. When I say the twisted schematic diagram of a 2-input NAND gate, first draw the normal schematic. So that it's easy for converting it into twisted schematic. So this is, let's say this is A, and this is B. This is A, this is B, this is the output Z, P1, P2, N1 and N2. So this is source, source, drain, 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 source, drain, source. These are the gate terminals. Now when you have to convert it into twisted schematic, as we have seen in the earlier lectures, twist it in this format. This is P1, this is P2, this is N1, and this is N2. So I want to name them. It's P1, P2, N1 and N2. The gates of P1 and N1, they are shorted. So okay, before that, can give the name. This is the source, this is the drain, this is the drain, this is the source, this is the drain, source, drain and source. So now the source of P1 and P2 are shorted to VDD. Source of P1 and P2, they are shorted to VDD, and the two drains are shorted, connected. Next, these two drains are connected to the drain of N1, or you can do one thing. Instead of connecting, it will be easier if we connect from here to here, from here to here. Okay. Okay, we can make it as, let's say this is N2 and this is N1. For this case, if I say this is N2 and let's say this is N1, so this drain will be connected to the, okay, before that these two gates are also shorted, so this drain will be connected over here, then this drain and this source are shorted. Okay, this source is connected to ground. Okay, if I make it as N1 and this should be actually N2, then you have to make some changes over here, okay, accordingly. So if I take this as the, actually when I take this as N2 and this as N1, then there will be just a change in the change over here. This will be connected over here. This is N1 and this will be connected over here. Okay, now this is connected over here. Okay, now this is right. This is a twisted schematic diagram of a 2-input NAND gate. Now let's see how to draw the layout from the normal schematic diagram of a 2-input NAND gate. Layout from the normal schematic diagram. So since there are two PMOS in parallel, they have a common drain point. So draw the anvil first. This is the anvil. In order to draw the P diffusion layer, we know that the P diffusion layer is brown in color. So we take the P diffusion layer. Okay, now the same area of the P diffusion, we need the N diffusion layer, which is green in color. So this is the N diffusion layer. And label the P diffusion layer. This is the P diffusion layer. Now after drawing the P diffusion and N diffusion layer, next you have to draw the poly. These are the two inputs, A and B. The output will be Y, the output will be Z. If you want to label the source and drain, this is the source terminal of P1, this is its drain terminal, this is the source terminal of D2, N2, this is source terminal of P1, this is drain terminal of P1, source terminal of P2, and this is the drain terminal of P2. So since these two are shorted, so we need not do anything over here. These are the gates. Similarly, this is the source of N1 and this is the drain. Here is source and this is the drain. These are the gate terminals. So now in order to make the connections, we need the metal layer. Wooden label the poly layer. So this is the poly layer. Now source, these two sources are connected to VDD. So this is VDD and this is metal 1. Okay, now the source here is connected to ground. Okay, now this drain is connected to this drain. So okay, this is the output, that is Z. A, B and Z output. Now in order to do the contacts, we need to place the metal contacts. So let's make it black in color. So there will be one contact over here. So this is the N diffusion contact. So this is the P diffusion layer or P diffusion contact, or you can term it as the PDC. This is needed in order to connect the metal layer to the diffusion layer. Similarly, we need one more contact over here. Now this is the P diffusion contact. Similarly, we need one more contact over here. This is another PDC contact. So similarly, we need the N diffusion contacts in order to connect the N diffusion layer with the metal layer. So this is the N diffusion contact. The NDC. Okay, then after placing the N diffusion contacts or the diffusion contacts, we need to place the substrate contacts in the sources, that is VDD and ground. So you can place this as many number as you can. So this is the N substrate contact, or you can say this is N well contact. Similarly, this is the ground. You have to label it as ground. So you need this is the P substrate contact, or the P well contact. So this is the layout of a twin port NAND gate from the twisted schematic diagram. Now let's see the layout from the normal schematic. So actually this was the layout from the normal schematic. The earlier that we had discussed, this was the twisted schematic. So we can erase this part. And you can write this as the twisted schematic. This was a twisted schematic, not from the normal schematic. So now we'll see the layout from the normal schematic diagram. When we talk of the normal schematic diagram, first we have to draw the two PMOS in parallel. So first draw the two anvils. This is the anvil. Now next we have the P diffusion layer, which is brown in color. So this is the P diffusion layer. This is the P diffusion layer. We write the P diffusion layer as pdiff in the commands in Magic. Then of the same area we need the N diffusion layer. So the N MOS are in series. So this is 1, and this is another one. or the end diff layer. Now let's name the terminals. This is the source, this is the drain, this is the gate. Similarly, source, gate and drain. This is drain, gate, source, drain, gate, source. So first connect the gates. So this is input A. Okay, according to our assumption, this is N2 now, and this is N1, this is N2. Actually we had to do this as N1 and this as N2. If you want, you can change it. Then this is second input, that is B, and this is the poly layer. Now after connecting the corresponding gates, connect the sources to VDD. The sources of the PMOS are connected to VDD. So this is VDD. This is metal 1. The two drains are shorted. They are shorted to this drain. Now the source is connected to this drain. Connect. This source is connected to ground. So this is ground. Now after drawing this, have to place the contacts. So we'll start with the diffusion contacts. So this is the P diffusion contact. Or the PDC. Similarly over here. Then similarly we have the N diffusion contacts for connecting the metal layer with the N diffusion layer. So this is the N diffusion contact or the NDC contact. Similarly, you have to place some substrate contacts. This is the N substrate contact. Or the NWC. This is the P substrate contact or the PWC. So this is the layout from the normal schematic of a twin port NAND gate. Now let's see another procedure for drawing this. That is using the cell instantiation process in layout. In Magic, we can use cell instantiation in Magic, since we'll be drawing the layout in Magic. Now when we say it is cell instantiation, what we will do, NAND, we know that NAND is a combination of AND plus NOT. We have drawn the layout of AND and also the layout for NOT. So if we call the AND cell has two inputs, A and B. Input Y is the output. This Y will be given as input to the NOT gate cell, where Y is the input, Z is the output. This is Z. So these are the cell instantiation process. And if you see in the overall way, so you get a NAND gate with input X, so input A, B and output is Z. Now how will you obtain this cell? There is a command in Magic called get cell. Suppose your name of this is and2, then you'll type get cell and2 dot your file. Then you have to press X in order to see the inner layout, then you can connect. So this is the process of cell instantiation, and this is not much followed in the layout process. So this is the third way followed in order to draw the layout of a NAND gate. In this schematic also we had A dot B. Actually we designed the A dot B, which in complementary form we obtain A dot B bar as the output. So this is all about the schematic and layout. And this is NAND and plus not is NAND.